Hello YouTube! Today we're going to be talking about simple harmonic motion. This is going to be the first part. Second part will be using pendulums and angles instead of using sort of linear stuff and springs. And we'll get to that next. But for now, we're going to sort of talk about the basics using simplest system that we can have for that. So, ideally, end of the day, you should be able to identify and model simple harmonic oscillators. So both figure out if something will be a simple harmonic oscillator or not, and then derive the equations for how it will move, including the period equation and all of the different kinematic equations for like where it'll be, how fast it'll be going, how much it'll be accelerating at different times along the way. The other thing, which I don't think that the example from this one is going to do a particularly good job of, is being able to think in terms of fractions of a period. So like 1/4 of the way through the period, where is it going to be and what's it going to be doing? And then at every interval of 1/4 plus 1 of the period, where is it going to be at? And sort of identifying that relationship. And then in particular, the big parts of that are identifying the locations and times at which you will have the most or least force or acceleration or velocity for the object. So, simple harmonic oscillators are anything that's moving back and forth in a cyclical or a patterned way with a very specific equation form. So there's a decent chunk of things that move back and forth. I don't unfortunately have a good example of a spring on me, but if you take a object on the end of a string and you let that swing back and forth a bit, it'll be following a pattern where it'll go all the way to one side, all the way to the other side, down to the middle, and back and forth. And every time it does that, that is an oscillation, or one repetition of the cycle. So a simple harmonic oscillator is a thing that is doing that in a very specific way. That's what makes it simple harmonic, or simple harmonic motion. The specific equation form that those things will follow is that the acceleration will be proportional to some constant times specifically negative position. And so what that means is your acceleration will be dependent only on where the object or the oscillator is. It will always be pushing back away from the direction that it's located, or accelerating away from the direction that it's located. And as it accelerates away from the direction that it's located, it'll get a stronger acceleration back towards that center location if it's further away from that center location. And if that happens, if that's true, then you'll get a simple harmonic oscillator. So the approaches, the thought styles, the things that we're going to be talking about now will only work if the equation form is that A is related to negative some constant times x. But it'll also apply to everything where acceleration is related to some negative constant times x. So when that happens, you get this really specific set of equations, and we're going to walk through how via differential equations that govern the way that the object moves. So for springs, we're going to pop over to paper because it's a little too involved for me to write out on the thing, especially without use of a second monitor. I really should order the cord to get that thing patched up. In any case, pen will work for now. So let's say we've got a setup where we've got a spring. And we know our force equation from the forces unit, where springs are negative kx, where we've got our spring constant. It pulls back towards the middle, and it gets stronger as the object is further away from where it started. Sorry, I'm still messing around with the lighting. All right, that should be good enough for now. So we'll have our object where when it's at its its location 0, in the middle, there's no force. When it's over on this side, the force will be directed back towards the left, and when it's over on this side of the center, the force will be pushing it back towards the right. And this situation happens a lot more often when the spring is actually hanging upside down. So like if I take something like these headphones again, where there's this little bit of a springy thing here, and this is too long to fit all on camera, and I let it drop and bounce up and down, that would be a situation like this, where there's this central location that it keeps getting pulled towards. When it's above it, it gets pulled down towards it. When it's below it, it gets pulled up towards it. So, in particular, if we want to figure out, so relevant for this derivation, and a lot of times this is the part that sort of really starts to lose people, what if that's not all we wanted to know? What if what we wanted to know was where the object was going to be at any given point in time? What if we wanted to know was how much the object is accelerating, how fast it's going? And in particular, something that's very relevant for simple harmonic motion that I just realized we never really talked about because we didn't have a waves unit, is period, as in the period of time it takes to do something, which is equal to the amount of time that it takes for a bunch of repetitions to happen, divided by the number of repetitions that wind up happening, and frequency, which is how often something happens, which is the number of cycles that it takes that something does divided by time, and that'll tell you how many times it happens each second. Those two are flipped, so period is equal to 1 divided by frequency. For today, we're mostly going to be focusing on period. So let's say you wanted to figure out where the thing's going to be at any given point in time, how fast it's going to be going at any given point in time, and how much it'll be accelerating at any given point in time. And you also want to figure out how long it'll take to complete one full pattern, one full back and forth. Oh my. So, that's our end goal. The problem is force is none of those things, right? We've found a way to figure out how much force is going to be on it based on a given location, but we haven't done is related that to when it is, how long it's taking. So to do that, I'm going to start by breaking up my force and thinking about it more in terms of acceleration. The force from the spring, if it's the only force that's on it, or if there's only a constant force on it other than that, because of the calculus we're going to wind up doing, will function such that it's going to basically be equal to the mass of our block that's tied to the spring, or attached to the spring somehow, times our acceleration. If we think of this a slightly different way, our acceleration is going to be equal to the second time derivative of our position. And so we've suddenly got this equation that's kind of special because our second derivative needs to be related to our original when we're not taking a time derivative. So our x double dot is equal to negative kx over m if we isolate our x double dot. Now, unfortunately, we can't just separate out the second derivative with respect to time, like multiply each side by dt squared, divide each side by x, and integrate twice, because that's not quite how these functions work. We sometimes abuse that. We sometimes try to get that to work and pretend it'll be fine. But for this one, that's not going to cut it. But if we spend a little bit of time thinking about how this function works, we can sort of arrive at the shortcut, and unfortunately you kind of just have to have this memorized. So, thinking about the function. If we do something along the lines of a substitution, where I say that k over m is going to be my constant, which I'm going to call c. What I've got is a situation where when I take the second derivative of the thing, I need to get back out negative some constant times the original function. And if you take a minute to think about functions where that happens, the first thing that for me would be helpful is to be like, okay, well, is there a function that gives me back something very similar to itself when I take a first derivative? And the first thing that comes to mind for me is like e to the whatever. That's not really going to cut it, specifically because we need that negative there when we take the second derivative. So you could think of something along the lines of e to the negative, e to the ix. If you take the first derivative, you'll get I times e to the x. If you take the second derivative, e to the ix. If you take the second derivative, you'll get the I twice. Having the imaginary number twice makes it positive, makes the 2 multiplied to -1, which would get you negative the original, and that would do it. This is actually a way of proving that e to the ix is equal to the other function that we're going to use instead. That's a little bit more familiar. And so if we're instead thinking about things that are 2 along the line, well, something that equals pretty much itself when you take a second derivative is a trig function. Because when you take the first derivative of sine, you'll get cosine, and when you take the derivative of cosine, you'll get negative sine. And that would pop you back out with exactly what you had, but negative. So either a sine function or a cosine function actually follows the equation model that this puts forward. The one thing that we have to be careful about here is we need to make it so that A, we get the correct constants in front of x when we take the second derivative, and B, that's, I guess, pretty much it. So if we want to find x as a function of time, we need to make it so that our x as a function of time works such that once we take the second derivative, we get negative the original function times some constant. Great. So let's sort of try to do that. If I take a cosine function and I put some arbitrary constant on the inside, and I'm going to use the letter D. That's times our time times some arbitrary constant that I'm going to call A for amplitude, and I'm going to say max, meaning our biggest possible value, and say that that's equal to x. Let's see if this meets the criteria of having our second derivative equal the thing that we had originally, but negative. If it does, the function works, and we can use that as our function to model x. Things to note here. I specifically picked cosine because I want to start it so that when we've got our time equaling 0, our object is starting away from the center. The reason I'm picking that is because a lot of times when you're doing things with these springs, you're pulling it back to a distance and then you're letting it go from that distance. And so it starts oscillating back and forth from a position that's already displaced. If you're bringing it behind the thing to start, you would want to start with negative cosine because you want your x at the beginning to be negative. If you're bringing it in front of the start, you would want your x at the beginning to be positive. Coming over here, if I take the derivative of this with respect to time, I'll get a velocity equation. My velocity equation will be a max sine of the inside of this times the derivative of the inside of this, which is just going to be, oh, I just realized that d is a terrible constant to have chosen. Yeah, I'm seeing why they use the one that they use. I don't really like it because it's got special significance in other places, but they tend to use omega for reasons that I don't super want to get into. I don't want it to look like a derivative, so I'm just going to swap it over to omega. Times omega. And that'll equal our velocity because we took a time derivative of position. If we take another derivative, we'll get our amplitude chilling at the outside times our cosine. Oh, sorry, this one should be negative because derivative of cosine is negative sine. Derivative of sine is positive, but that negative is still on the outside. With an omega squared now. If we look at this, our acceleration is equal to our x double dot. Quick thing, I chose to have a max be the thing that's multiplied by cosine because the biggest value that a cosine function can have is 1. The problem is you're not always displacing a spring by 1 meter. You're displacing a spring by a variable amount of distance. And so this A max right here makes it so that when we have our cosine be 1, we're at an x position such that we're all the way stretched out at our maximum distance that we've traveled. So this distance here would be A max. Great. So now coming back here to see if this equation fits this equation form that we were shooting for. Well, let's take x and substitute it back in over here. The thing that equals x is A max times cosine omega t. So negative x times omega squared will equal x double dot. Well, that's great. This is a constant. And what this represents is our phasing, or not our phasing, our period function, or our period value within our cosine function. Because it's not going to be such that every 2 pi seconds you finish a complete rotation. It's going to be something varied based on that. We multiply and include this omega in here to make sure that when we actually have our final answer, we're accounting for the fact that there's going to be different amounts of time that it'll take to finish. We could include also like a phase shift, so we could do plus phi for the amount of phase shifting that we want to apply. So like if at time 0 it doesn't start right all the way on the right, if it starts in the middle, or if it starts all on the left, or it starts in the middle going to the right instead of the middle going to the left, we could include that phase shift, and sometimes people do. For me, I think it's easier just to be careful about if it starts in the middle, I want to use a sine function. If it starts on the edges, because the x position should be 0 when the time is 0. If it starts at the edges, I want to use a cosine function. And just being a little careful there. Generally speaking, it's not going to make a big difference which one you pick, as long as you're careful about dealing with your phase shifting once you've done it. So we've got this constant that's in front of x. Well, previously when we looked at our equation, our constant was c, and in fact our constant was k divided by m, some actual physical values. What that means is that this function that we picked works, and it works just fine, but it only works if the constant that's being multiplied by x is the same thing as omega squared. So that tells us that k over m is equal to the thing inside our sine cosine function squared. So if we want the thing inside our sine cosine function, we square root both sides, and we'll get that our thing inside our sine cosine function is equal to k over m. If we take that and plug that back into our 3 equations, we'll get our 3 equations that tell us where this object's going to be at any given point in time without any weird arbitrary constants. Like omega, which is like, it's a scaling factor that cosine functions always have. So our x equations, so final equations, are that our x position is going to be our amplitude at the maximum times cosine of the square root of k over m times our time. Our velocity is going to equal our amplitude times the square root of k over m for 1 omega times the sine, negative, of square root of k over m times t. Our acceleration is going to be negative our maximum amplitude, or our maximum location, which we could just be calling x max. I don't know why I chose a max. I guess just to stress that the vocab word is amplitude, times our omega squared, which again, our omega squared is just k over m, or root k over m times root k over m, so k over m. So k over m winds up being our thing that's in front of our brand new cosine function. And these are sort of our final three equations. The last thing that we can do is think about how a sine or a cosine function works. Well, every time the inside of the function reaches 2 pi, we'll have completed a full cycle of sine or cosine. And so that means that the amount of time it takes to finish needs to be such that if we plug the amount of time that it takes to finish in for t, we will get 2 pi. So whatever's inside the cosine function, when we plug in t as our period, needs to equal 2 pi. So 2 pi will need to equal the square root of k over m times our period. So if we're looking for how long it takes to complete a full cycle, we need to get rid of root k over m, which we can do if we multiply by root m over k. When we do that, our final period will be equal to 2 pi times the square root of m over k. And that's our sort of last big equation here. Few things about this. What this means is that the amount of time it takes for a simple harmonic oscillator to finish a complete cycle depends on how heavy the thing that's on the spring is and how strong the spring is. And that's it. This tends to be a little counterintuitive for people because it doesn't depend on the angle that you have it at. It doesn't depend on the amount of that you pull it back either, which to me is the weird one. Because in a sense, if you pull it back, it should make it take longer, right? It's got more distance to travel, and so when you pull it back further, it's going to take more time to travel that much greater distance. But there's also a reason why it should take less time. If you pull it further back, it's getting pulled by the spring harder towards the middle. So the acceleration will be greater. And so because the acceleration is greater, the average velocity at any given point in time will also wind up being greater. So yes, you have a greater distance to travel, but you're also going faster. And it turns out that those two things perfectly cancel each other out, such that the maximum amount that you pull it back doesn't actually affect anything to do with how long it takes to happen. What it does affect is how far you go. What it does affect is how fast you go. What it does affect is how much acceleration there is at any given point in time. But it doesn't affect how long it takes for the spring to finish one complete period. If we think about what these things look like while graphed, our position graph will look something like this, where it starts at a location and then gets big and then gets small and then keeps going. If we think about our velocity graph, it'll look something like this, where it's starting at 0 when we're at our maximum, and then our velocity is pulling back towards the center, and then we hit our minimum velocity when our position is at a 0. Then when our position is at our maximum, we get back, negative maximum, we get back to a velocity of 0. And then when our position is at 0, we are at a maximum velocity, followed by 0 when we're at our maximum position, followed by our maximum when we're at 0, negative maximum, followed by our 0, and so on. Where one's a cosine function, one's a sine function. Something I do briefly want to highlight here, we'll wait till we've got it all. For our acceleration graph, it'll look much like our position graph did, but instead of being such that our values are positive, now our values will be negative because we have a negative cosine function. So we'll have something like this. Feel like I missed. Oh yeah, I did miss something, the last one. So, some takeaways from these graphs and some takeaways from these functions. When x is at its maximum, that tells you that velocity is going to be equal to 0. That should make some level of sense. When the spring is all the way stretched out, you've got all potential, no kinetic. That's the reason why it stops, is because we've translated all our energy from kinetic into potential. But that's also the place where you have the biggest positive x displacement. That means you're going to have the most force pulling the spring back towards the middle because you're the furthest away from the middle and the spring really wants you to be back in the middle. So our acceleration will be at its negative maximum. Meanwhile, when our x is at 0, our acceleration will also be at 0, but our velocity will be such that it'll either be at its positive maximum value if it's going from the left to the right, or its negative maximum value if it's going from the right to the left. Which I know I just did the same hand motion twice. I realized that the camera's flipped after I did it the first time. So our velocity will be its plus or minus of its maximum. So that's something to bear in mind. Another thing to bear in mind is that one full repetition is one full period. 1/4 of the way through the period, 1/2 of the way through the period, 3/4 of the way through the period, and then 4/4 of the way through the period, you'll be at these sort of major points. What you can then also do with that is add 4/4 to any of these. And if you're at 5/4, if you're at 9/4, if you're at 14/4, nope. No, yeah, 13/4, not 14/4. Then you'll be at this same position where you'll have no acceleration, negative maximum velocity, and no position. If you wait until you're at 7/4 of the way through, you'll again have no acceleration, but this time you'll have a positive maximum velocity and no minimum position. Whereas if you wait for a half period or a full period plus or minus 4/4 of a period on either of those ends, you'll be at a place where you have positive or negative maximum acceleration, positive or negative maximum displacement, and no velocity. Whew, that was a lot of talking without actually doing any example problems. So key takeaways here. When you see something so that the second derivative needs to equal some stuff times the original first derivative, what you can do is you can set up a trig function so that your biggest possible value times cosine times some scaling factor to get the period to work out correctly times time will need to equal your position. When you take the second derivative of that, you'll get back out that your scaling factor squared is now that constant that's in front of your original function. Because of that, whatever was originally in front of your non-derivative form, that's going to be equal to your scaling factor from inside your sine or cosine function squared. Because that scaling factor, which means that your scaling factor will equal the square root of the stuff that's in front of your base function. Because that scaling factor times a full period will need to equal out 2 pi for the cosine function to have completed one full cycle in that time, you can then solve for the period of the function by just solving that setup for t. So, that's sort of the approach we took. And anytime you have something that looks like it might be a simple harmonic oscillator, basically anything that you're like, hey, the second derivative of this is equal to no derivative times some constant, but negative. That but negative part is huge. If it's not but negative, it's a different type of differential equation that we talked about a while ago that's actually much harder. Go figure. Then you can use this setup. Half an hour later, and we get to start the example problem. Thankfully, it's the only example problem. I have no idea how long it is. I am flush with graph paper. Okay. So, a student takes a cart that's hooked up to a spring B with a spring constant of K. The student displaces the cart away from the resting state of the spring by a distance of X, then lets it go. The student repeats the process with a new spring with a spring constant of 4K. Great. So spring constant of K is going to a new spring constant of 4 times K. A, what happens to the maximum displacement? B, what happens to the period? C, what happens to the maximum acceleration? And D, what happens to the maximum velocity? All right. There are a lot of ways that you could approach these. I think for me, the one that makes the most sense is to look at our 4 equations that we had and just kind of set up a general proportionality field. The one thing that's going to make it weird is that your sine and cosine function are going to be a little bit of thinking for your proportionality stuff, but otherwise, basically the same as what we've been doing so far for proportionality when it's occasionally come up. So for our x equation, x is equal to our amplitude times our cosine of k over root k over m times our time. Yes. Great. Well, if we multiply k by 4, what happens to our maximum? Well, the inside of the cosine function doesn't change how big a cosine function can get. The biggest the cosine function can get is 1 or -1. So our x max is going to occur when our cosine function is equal to 1. Which means k doesn't factor into that. It's not part of it. X max isn't proportional to k. They're still pulling it back the same distance. And so it's still going to go back and forth between, well, the same distance. So that tells us that for A, there's no change. For B, if we set up our period equation, period is equal to 2 pi square root of m over k. That means that our period is going to be proportional to the square root of 1 over k, because all of our other factors are staying the same. If I plug in 4 for k, what that tells me is that my period will be related to 1 over 4 square rooted, which is 1/2. So our period will become half as big if our spring gets twice as strong. At every single point along the way, it's getting a greater acceleration because it's getting a greater force because it's getting pulled harder by a spring. So it takes less time to go. Great. Now for C. For C, we're using our velocity equation. Well, our velocity is equal to our maximum acceleration, derivative of this one, so negative, times root mk over m. Keeping track of which side has the m on top and which side has the k on top can be a big old pain. You do still have to do it though. Square root of k over m times t. Once again, sine cosine function isn't going to matter, just like for location. But the big difference here is that our velocity maximum will be equal to our amplitude times the square root of m over k. One place that this is coming from that you could also use to conceptually solve this, we'll deal with in a sec. For now, let's just finish out this way. So we're trying to figure out what happens to Vmax when our k changes. So in this case, k over m. Geez. K over m. In this case, we've got Vmax will be related to root k. The m isn't changing, so I can ignore it. The amplitude isn't changing, so I can ignore it. If we sub in 4, we'll get that Vmax is going to be related to the root of 4, which is equal to 2. So our maximum velocity gets twice as big when we get 4 times the spring constant. You could also approach this one just straight up with energy. We've got 1/2 kx squared, the potential energy it has at the beginning, will need to be equal to 1/2 m Vmax squared, because the maximum amount of velocity will be happening when all of our potential energy from the beginning has been turned into kinetic. If we're looking at that, then what we can do is just say that k is going to be related to Vmax squared, and we very quickly arrive at the same place. This way in particular is really useful for when it's asking about velocity not at the maximum, because you can conceptualize that as some amount of velocity or some amount of energy that's been given to potential versus kinetic. Sometimes it can be really helpful to think about it as like a fractional amount of the energy. When it's halfway towards the middle, I think that would mean that you have 1/4 as much potential energy. So 3/4 of that total energy from the beginning will be kinetic, and you can use that to sort of figure out your relationships there. So sometimes it's easier to think of it just by using the equation. Sometimes it's a little bit easier to think about it by going back to our older ways of approaching it and using energy. For D, similar things. Oh, I accidentally did D instead of C. This is D. For C, similar things where you could just use the force equation. You know that acceleration maximum will be happening when you're at your maximum displacement. So you could just use proportionality off the force equation, or you can use our new equations and approach it as acceleration is equal to negative A max times K over M times the cosine of root K over M times T. You're again finding it when your cosine is equal to 1, which means that your acceleration will be equal to negative A max times K over M. This is what you get from the force equation as well, so it's just sort of one step away from using it with forces. And that tells you that your acceleration will actually just be directly proportional to K. If K is 4 times as big, you get 4 times as much acceleration because your spring is 4 times as strong, so your force is 4 times as strong. Mass hasn't changed, so there you go. And that's a little bit of everything. Some of it was in the form of solving a specific problem, some of it was in the form of me incoherently babbling. Such is life. Hope that helped. Goodbye, YouTube.